Hey guys, it's John from THKP, and today we're going to be doing Fruit Ninja. Now, if you exist in the same universe, you've probably heard of Fruit Ninja, but just in case you haven't, it's a game where you play as a ninja, you have a sword or something, and some guy's throwing fruit at you, and you have to slice the fruit in half before it hits the ground. It's a super addictive game that was popular maybe 10 or so years ago, and I just want to show you the basics of how to make it in Flutter. So let's hop right in and look at where we're starting. We have our app here, Fruit Ninja app. It's just a simple scaffold, got a container with a gray background. We're not going to be doing anything visually stunning with this project because there is enough to cover without all of that, so I'll leave that to you as homework. And then we have a layout builder here, and this is just so that we can get the size of the screen. Screen size and world size, these are the two transformations that we're going to be using for our game. So you'll see code that translates between screen size and world size. All of the physics logic will take place in world coordinates, but when we're drawing to the screen, we'll have to translate into screen coordinates. So that's why we need both of these sizes. We'll just pass them into our Fruit Ninja widget. And in here, it's dead simple. We store our two sizes. Inside of our state, we're just returning a centered watermelon for now. So let's go over to model. Model is where we're going to define all of our important classes that we're going to use, all of our fruit, slices, things like, a piece of sliced fruit will be defined here. So let's go ahead and define some of that. First thing we're going to need is a fruit type. And I like to create extensions on my enums sometimes, especially if I'm going to be tying certain information to the enum. So let's create a nice extension here. Each fruit will need a size, and once again, this is in world size. I'll actually just call it world size. So you might wonder where all these crazy numbers come from. This is really just based on the size of the image. If I show you the images, you can see that the width is not equal to the height, which is why going back to this model, you'll see that these two numbers are not exactly equal. I just use the same ratio. And then this 2 is more or less arbitrarily chosen. But if you remember from the world height, it's 16. So a height of 2 will be roughly 1/8 the height of the world. So I just like that as a value. I think it looks pretty good, so that's why I'm using it. So we'll also provide a method to get the actual image file. And then I will also provide a convenience method to get an actual image widget based on if you just have a fruit type. And once again, we're going to be translating from world space to screen space. So I'm going to pass in a pixels per unit here. And this is pretty simple. We're just going to be using our world size and multiplying by our pixels per unit in order to get the actual width and height of the image. So just a simple transformation from one space to another. Next, I'm going to define our piece of fruit. This is just one of the fruit that gets thrown at you. I'm going to have a key. There's going to be a lot of animated widgets in this game, so I'll be using a lot of keys so that Flutter can uniquely identify these widgets as I'm adding and replacing them. If you didn't have keys here, Flutter will get confused about which widget is which, and animation progress might get lost, and you'll see just weird bugs. So keep this in mind if you're seeing strange bugs, if you're replacing items in a list or replacing items in a stack. You might want to consider trying to use keys and seeing if that helps your issues. So for a piece of fruit, I'm also going to store the time when the fruit was created. And we'll see why a little bit later. The basic idea is I want to be able to calculate where the fruit is in the world space at any given time. And you can use some basic functions for trajectories of thrown objects. In order to calculate where the fruit is, you just need the initial time. Next, I'm actually going to create something called a flight path, and I haven't created it yet, so it's red underlined. And we'll describe what a flight path is in just a moment, and then I'm going to have the actual type of the fruit. So let's create a constructor. All right, And next, I want a sliced fruit. And this could be the same class, but I'm making it a different class. This is basically a fruit that's already been sliced. And this is just kind of a personal preference. This could definitely, we could reuse the same class or, you know, have like a sliced Boolean here, but I just prefer to do it this way. So let's create another unique key, because once again, we're going to be tracking these things. Now, this is interesting. Later on, we're going to see exactly how this works, but I'm basically using a polygon to represent where the fruit was sliced. Like if you slice this watermelon right here, then you'd have this, you know, polygon that almost looks like a triangle, but, you know, has this little part here. And that would sort of dictate which part of the watermelon is getting rendered for this sliced fruit. So that's what this means right here. It's basically the polygon of the image that we are rendering. You'll see how that works in a little bit. So this also has a flight path. Even after you slice it, it's still going to be a moving body, so it'll have a flight path. And let's create our constructor. We're also going to want to represent slices on the screen. So as the user, you know, clicks and drags on the screen, he or she is going to be slicing the screen. And we just want to represent those, both for physics calculations, and also we're going to be displaying the slice. So for those reasons, we're going to need to be able to represent these. This is simple. It's just 2 offsets. Now, by the way, I should say when you're doing physics calculations and things like that, it might be a good idea to just import the vector library. That's usually a better library to use for things like position data, because they allow you to do dot products and cross products, and it's probably more performant. I'm using offsets just because I didn't want to, you know, add some additional thing that people might not be familiar with. But just be aware that there is Flutter has a nice vector library. You just have to import the library, and it has nice vector classes for things like physics, math. For our purposes, since we're doing relatively simple stuff, offsets will work perfectly. So that's what I'm going to use. All right, now finally we'll define our flight path class. So this is going to be interesting. It's basically all of the properties of a flying object. So a flying object has an angle. This is going to be kind of a starting angle. It has an angular velocity. It has a position. And once again, this is kind of going to be a starting position. And then it has a velocity. And then we'll just define a few methods. Get position will be one of them. And here you just pass in a elapsed time. I'm just going to call it t. And if you remember some of your physics from school, you'll know that you can calculate the position of an object by taking the gravity divided by 2, or times 0.5, that's the same thing. Multiply it by t squared, which is just t times t, and then add in the velocity, multiply that times t, and then add in the initial position. So this formula right here will give you the current position. So, and just for the sake of a little bit of neatness, we can just do that, make it a one-liner. Now we want to get the angle. This is a very, very similar concept. It's even simpler actually. We just have our initial angle plus our angular velocity, and then times the elapsed time. That's it. And next, I'm going to do something that's a bit more complicated. We're going to have a function to get our zeros. So you might remember this. If you throw an object in the air, it creates a parabola. And there's 2 points on the parabola that intersect with the x-axis. And this isn't always true. Obviously, if you're already in the sky when you throw an object, then, you know, the initial position won't intersect with the x-axis, because the x-axis is the ground. But in our case, our objects are going to come from below the screen, you know, fly up, and then fall below the screen. So all of the objects in our app will have 2 zeros. And how do you calculate zeros? Well, you might remember an equation from school called the quadratic formula. You probably thought you'd never use the quadratic formula. Well, here it is. Negative b plus or minus the square root of b squared minus 4ac over 2a. And what are all those terms? Well, in our position equation, so let's just create a comment here. Position equation, we have a times t squared plus v, we'll call it b, times t plus c. So these are all the terms of the quadratic formula, a, b, and c. So a is just equal to gravity times 0.5, and it's just the y value, because by the way, we only care about the y value here. We do not care about x. We're just interested where the y value intersects with the x axes. Next, we need to calculate our square root term. So obviously, we're going to use square root here. So this is b squared, and then minus 4ac, so 4.0 times a times, and then c, once again, is just our position. And now we know that the answers are, so negative b, which is our y velocity, plus the square root term, and then all that quantity divided by 2 times a. And then there's a second answer, because if you remember, it's plus or minus, which is just minus the square root term. So these are our zeros. And we're going to be using this a little bit later when we're determining how long an object is on the screen, because the larger of the 2 zeros will be the duration of time that an object is on the screen. Okay, let's throw some objects in the air. I'm going to create a widget called flight path widget. As you might imagine, this object will take a flight path as an argument, and it will take a world size and a pixels per unit, because this has to draw it on the screen, so I need both of those pieces of information. Then it will take the actual widget that's flying through the air. And finally, I want to provide a function that will be called when the widget is done flying through the air. So I'll just call this on off screen, which sounds a little weird, but it's just an event that fires when the object falls off the screen. So in our widget state, this will be pretty straightforward. We're going to use an animation here. So let's create an animation controller. And as usual, we're going to use single ticker provider state mixin. Now, this animation controller is going to be a little bit different from normal. We want the animation controller to go from 0 to the total amount of time this object is flying through the air. So how do we get that total amount of time? Well, we just created that zeros function. Let's use it. So we'll get our zeros off of our flight path. And then, as I mentioned before, the max of those 2 zeros is going to be the amount of time that the object is flying through the air. So under here, we have to do 2 things to allow an animation controller to go beyond 1. First, we set the duration like normal. We use milliseconds, so we'll just multiply this, which is in seconds, by 1,000. And then we also have to set an upper bound, and we'll just set it to our time. And one other minor thing I want to do is I just want to give it 1 extra second of airtime. I need to import math here. So I'm just going to say time plus equals 1. And that's just so it has enough time to fall completely off the screen. Next, we just want to add a status listener to this controller. Add status listener. And when the status is completed, then we'll call that function that was passed in. All right, and then we go ahead and just start our controller forward. And in the build method, we just need an animated builder. The animation is going to be our controller. So here is where some of those methods that we added to flight path come in handy. We can grab our position from the flight path. And since our controller is going from time 0 to the time when it's off the screen, we can just simply use our controller's value. And we're just going to return a positioned widget here. And all of the widgets in this app will be starting from the bottom left. So that's kind of our 0, 0 point. So I'll use left, position, dx. We got to subtract our widget's world size times 0.5. So we're just centering our widget at this position. So we're subtracting half the widget's width. And then bottom. So then the child of this positioned is going to be a transform because we want to rotate our object. So inside the transform, our matrix is just going to be a simple matrix, rotation Z, because we're sort of rotating. The Z-axis you can think of as shooting directly through the screen. So since we're rotating around that axis, we'll just say flight path, get angle. And the alignment is going to be alignment center, which means that this transform will take place around the center of the object. I find that alignment center is usually what I want. And then the child will just be the child of the gravity object. So let's hop back over to main and add some fruit to our Fruit Ninja widget. We'll have a list of piece of fruit. I spelled piece wrong, P-E-I, P-I-E. And in our init state method, what we can do is just create a periodic timer that will launch a piece of fruit into the air every so often. So we'll do, let's just say every 2 seconds. We'll call set state and we'll add to our fruit. Piece of fruit. And remember, we want to store the created time. And I'm actually going to go back here and make these kind of named parameters. I just prefer that a little better. All right, back to our main. So we have our created. Let's also include our flight path. And for this, I'm going to copy over a flight path that I've been using. And for the type, we'll just randomly select a type. And the way that we can do that is just say values. We need a random number generator, but once we have one, this will work. So fruit type, values length. Let's create a random number generator. All right, and then let's talk about this flight path just for a second. So the starting angle, this is more or less randomly chosen, but just so long as it doesn't start, perfectly like in line up and down or left and right, I think that looks a little weird. And then we just create a little bit of a angular velocity. Could be as much as 1/2 rotation per second. I just think that looks nice. And then for the position, we're actually going to start the fruit randomly along the bottom edge of the screen. And these are just random numbers, but they kind of work well. So it'll have an upward velocity of 7 and up to a max of 14, which just kind of looks good on the screen of height 16. So you'll see what it looks like. You can definitely play with these values and get some cool results. These are more or less arbitrary. So let's actually add these to the widget. And the way that we're going to do that is, firstly, our main widget is going to be a stack. And we'll just call this stack items. And what we'll do here is just iterate over our piece of fruit. And we can go ahead and add a flight path widget. So what do we need for this? We need a world size, and this is actually on the type of fruit. We need a pixels per unit, and this can actually be stored, or we can just create this in the build method, because the pixels per unit is just going to be the screen size divided by the world size height. Okay, we also need a child, which for this I'm just gonna say the fruit type and get image widget. Once again, we need our pixels per unit. And finally, we need when the fruit goes off screen. So on off screen. And what this will do is just remove the fruit. So simple. Fruit.remove F. Okay, so let's restart this app. Okay, here's some fruit. Now it looks like they're kind of just sitting in the bottom left corner, so there's clearly something wrong here. Yeah, so this position is in world space. So we actually need to multiply by our pixels per unit. All right, here we go. We have some fruit flying up in the air. Let's just restart. I'm not sure why that apple's there. It's kind of strange. Okay, so some of the fruit is just disappearing. It's a little weird. So let's try to figure out why that's happening. Oh, okay, I'm actually glad this happened because this goes back to what I was talking about earlier with keys. So you can see that we're removing this fruit and Flutter's just getting a little bit confused about, oh, I have this many objects in the stack and each object in the stack corresponds with one of these flight path widgets, which is why if you provide a key, all of these issues basically go away because Flutter is able to uniquely identify, that was amazing by the way, but Flutter is able to just uniquely identify which object is which, even when things are being added and removed from this list all the time. All right, so we now have our fruit flying up and down in the air. Let's talk about slicing the fruit in half. Before we write this line slicing algorithm, let's just talk about it for a second. I created this amazing diagram, which will help us out. So you can imagine the piece of fruit, and you can kind of draw an imaginary box around it. And this box is just centered at the origin. Let's pretend the origin is right in the center of the fruit. And the size of the box is just the world size of the fruit. And then you imagine this line, and this line is where the user clicked on the screen. So they click down, they drag their finger, and they click up. We do need to translate this line from screen coordinates into world coordinates. So you'll see that we do that. And then once we have all of this information, we can just iterate over the corners of this box. And for each of these lines, which you can see that 2 lines are perfectly vertical and 2 lines are perfectly horizontal, we can just calculate these collision points. And this is just relatively simple line collision stuff, especially given that this line is all the same x coordinate and this line's all the same y coordinate. And you'll see that that just makes our lives a little bit easier. And the end goal is to calculate these 2 polygons. So once we have these polygons, we can just pass these into a clip path, which is a Flutter widget, and Flutter will draw this watermelon image, except it will clip it based on this path. So what you'll see is we'll just draw 2 copies of the watermelon image. One is clipped with this orange polygon and one is clipped with this bluish polygon. Now you might ask, during the game, the fruit is rotated with some crazy angle. So how do we get this nice axis aligned box? Which, by the way, when a box is sort of these lines are perfectly straight and they're aligned with the X and Y axes. You'll often hear the term axis aligned box to describe that. They just make a lot of these calculations way easier. So that's why we're doing it. Anyway, during the game, the fruit is, spinning at some arbitrary angle. So the first step of this algorithm will be to take this line and anti-translate it. So we're basically taking, everything and we're translating it into the local space of this watermelon in order to make our lives easier. So let's go ahead and write the algorithm. So let's say slice math. All right, so let's write our function. It's just going to return a list of offsets is just the polygon. It's going to return a list of lists because there are two. As you see in this diagram, there's two polygons. So the result is either going to be two polygons or, if the line is way out here somewhere, there's no collision, so it's just going to return 0 polygons. So yeah, we'll just call this get slice paths. So offset 1 is the beginning of the slice. This is the end of the slice. This is the world size of the fruit. And this is the world position of the fruit. Oh, and we're also going to need the angle. I'll just call this size and position. All right, so as I mentioned before, the first step in this algorithm is going to be to rotate the points. So we need to write this function. And again, these are returning lists, but really they're just going to return 2 items. So we have almost the same parameters, except we don't have a size. So to rotate points around a position, you need the sine and cosine values. And then you can find the local points by basically subtracting the position of the object. And this kind of centers the points around the origin. You can think of it that way. And once a point is centered around the origin, you can just multiply in the sine and cosine in order to get a rotated point. And this probably looks crazy, but this is just how you rotate a point around the origin. So let's rotate our second point around the origin. And then we just need to add back in our position. Because earlier, we subtracted it right here, so I'm just gonna add it back in. Okay, so these points are now rotated. We also need the direction of this line, which is just the second point minus the first point. And by the way, the equation for a line is the beginning point, which in our case is L1, and then plus the direction times some t value, some interval value, and t goes from 0 to 1. Anything beyond 0 or 1 means that the point is off of our line segment. All right, now we just need a rectangle that represents the box in world space, and this is just a from center. And then we need the bottom of the top. And this is slightly weird, but Flutter has the top of the box is a lower value than the bottom of the box because Flutter starts at the top of the screen and values increase as you go down. We are going to reverse that. I like to think about geometric problems in the Cartesian space where y values go up as you move upwards. So I'm going to reverse this box's bottom and top. Next step, we're going to define the 2 paths of our polygons. They'll start as just empty lists. And then our current path will just start at path 1. And our current path is going to change as the algorithm proceeds every time we find a collision. And let me just show this image again. So every time we find a collision, we switch our path. So we'll start at path 1, which is the orange path. We find our first collision. We're going to switch to the blue path. We add this point. We find our second collision. We're going to switch back to the orange path. So our blue path is complete at that point. And then we just proceed with the orange path. So you can see that the path will kind of alternate whenever we find a collision. Another thing we're going to know or need to know is whether the current line is horizontal or not. We'll start it as false because the first line we're going to do is this left side of the box. And this horizontal value will just alternate as the algorithm proceeds. So then we're just going to iterate over the 4 corners. So this is the lower left, this is the upper left, upper right, and lower right. We're going to first add the corner to our current path. Then we're going to find our t value. And by the way, this t value is this from the line equation. And in order to find our t value, we can just simply do some algebra here. So L1 plus dir times t is equal to some point on the line. So if we're trying to find t, but we already have a point on the line, we can just move L1 to the other side. So dir times t equals point minus L1. And then we can divide by dir. So t is going to equal point minus L1 divided by dir. So let's do this math. So our t value is going to depend on if it's horizontal or vertical. If it's horizontal, we're going to want to find a collision in the y direction. So for all of these values, we're going to use the y part of our coordinate. So corner.dy minus the beginning of the line.dy, all divided by the direction.dy. And then if the line is not horizontal, meaning it's vertical, we're going to use x. Okay, and once again, this value has to be between 0 and 1. All right, and then the goal here is to find the cut point, which I'll call CP. The cut point is just this point and this point. And as you can see, sometimes there isn't a cut point. So if the line is horizontal, our cut point, we can plug all of our values back into this equation in order to find the x value where our cut point takes place. We need to make sure this x value is within the box, so it's greater than the left side of the box and less than the right side of the box. And if this is true, then we have a valid cut point here. So the cut point's x val is just going to be the x val, and the y value is going to be the corner's y value. And the reason it's the corner's y value is because, as we mentioned before, the y value, this is a horizontal line, so the y value is always the same, so we can use the corner's y value. Okay, and then similar, if the line is not horizontal, let's just copy this, although we're going to switch everything to y. So instead of x val, we're going to have a y value here. These are all y. And then the cut point is just going to be the corner's x value, and then our y val. So then if we end up finding a cut point, because we may not, none of this may be true, so this will still be null. If we do find a cut point, then we add the cut point to our current path. Oops, I put this in the wrong if block. So if we do find a cut point, we add it to our current path. We switch our path. So we just alternate paths. And then we also add the point to the other path. Because as you can see, if it's a cut point, it's going to appear in both paths. So we find the cut point, we add it to the orange path, we switch to the blue path, and we also add it to that path. All right, and then finally, we just need to make sure our horizontal is switching. So horizontal is equal to not horizontal. All right, and the last step is we just want to normalize everything. And the reason for this is we're going to return points that are all in world space, but we will eventually want those points in screen space when we're actually doing the clipping. So instead of, having these world points and then later converting them to screen points, I'm just going to normalize everything from 0 to 1, and it'll just make my life a little bit easier later on down the road. So to normalize, this is pretty easy. For every point in our path, we just return the x value of the point minus the box's left over the box's width. And then to normalize y, we do the y value minus the bottom over the box's height. This will give a value from 0 to 1, but as I mentioned earlier, Flutter starts at the top and goes down. So we actually want to say 1.0 minus this. Okay. So, all right, and then we just normalize the other path. So path 2. Then we just return them. So if their length is greater than 2, meaning it's at least a triangle, and path 2's length is greater than 2, then we just return a list of both of these paths. And when we're returning them, we have to make sure to add the first item in the path to the end, and I'll show you why in just a second. So path 2, add path 2, first item. And then if they're not both triangles, we just return an empty list. So this means that the fruit has not been sliced. And just to make this a little bit more clear, I'm just going to put this up here. So path 1, add the first point, and path 2, add the first point. And I'll show you why we do that in just a second, but then we can just remove that from here. Okay, so the reason we have to add back this first point, if we go back to our diagram, is we're drawing these two polygons. We're only going over the box one time. So let's just consider this blue polygon for now. We're gonna find these 2 points and then this third point, but then we're just gonna keep going. So when we're finished with the algorithm, we have this kind of incomplete polygon. So in order to complete the polygon, we just have to add back this first point. So, and that'll be the same for this orange polygon. We're gonna find this, we're gonna add this, we're gonna add this, and we're gonna add this. So we need to complete this line, so we just have to add back the first point. So that's why we do this funny business right here. And then if both paths are greater than 2 points, then we return them. Otherwise, no slice. So let's go back to main and slice some fruit. So first thing we got to do is add in a gesture detector. The child is just going to be our stack. We're going to change the behavior of this gesture detector to translucent. And this is because we just want to be able to click on areas where there's nothing underneath. So this will make basically the whole screen will be clickable. We need to implement a bunch of on-pan stuff. So when we pan down, we're just going to set our slice begin position. This will be where the sword slice starts. So slice begin position, And this is in screen space. So local position. So we need to add a variable to store this. And we're also just going to add a slice begin time, because we just want to make sure that the slice occurs within like a reasonable amount of time. And as the pan updates, we're going to set our slice end. And we're only going to finally look at it on pan end. So when on pan end happens, let's just grab now. And we want to make sure the slice took place in a reasonable time. So let's say now minus slice begin is less than, I don't know, let's say 750 milliseconds. And let's also just make sure the slice is big enough to be a reasonable slice. So slice end position minus slice begin position. We can use distance squared, slightly more efficient. And let's just say this is greater than, I don't know, 25. That's actually an extremely small size, by the way, because that means that the line is only 5 pixels long. So this is very permissive, but that's okay. Okay, so if these are true, we're gonna do a set state call here, because at a minimum, we're going to be adding a slice to the screen. I've mentioned before that you need to convert these slice points to world points. So let's just say, I'll just call it world begin. So it's gonna be a new offset, slice begin position dx. We just need to divide by the points per unit, or pixels per world unit, which I thought I had. Nice. And then for the y, we just want to do our screen size dot height minus the slice begin position. And let's add some new lines here so you can see what I'm typing. And by the way, the reason we're saying height minus this again is because we're actually flipping the y value. Instead of starting at the top and going down, we want to start at the bottom and go up. And this is kind of a personal preference on my part. I like thinking of geometric problems in terms of the Cartesian plane. So you don't necessarily have to do that, but that's what I'm doing. So the world end is going to be just the slice end position. Same translation here. So now we need to see if this slice actually intersects with any of our fruit. So let's go ahead and calculate the direction of the slice. And let's figure out which piece of fruit we're going to remove. And these will just be fruits that are getting sliced, because we're going to remove them. So let's iterate over our fruit and figure out which ones are destroyed. So for each fruit, we need to calculate exactly where it is. And we can do that by just getting the elapsed seconds. It's going to equal now minus the fruit's created time. You might remember we store this created time, and this is why. We divide it by 1,000 because everything's in milliseconds. And we can get the position of the fruit. And we can get the angle of the fruit. And then we can use our handy dandy slice method to get our slice paths. So if our slices is not empty, we're going to go ahead and remove the fruit. But as we're removing the fruit, we want to also add some sliced fruit. So I'm actually going to go ahead and add another list here, right below this guy, and this is going to be our sliced fruit. So when we slice a fruit, we're going to go ahead and add a new sliced fruit. It's going to mostly copy values from our actual fruit with some slight additions here. For one thing, we got a slice, which is just going to be the first item in our slices. By the way, we're going to add two. So the first one's going to be the first item, and the flight path of this, it's going to be very similar to the flight path of the fruit, except with just some slight modifications, which I'll show you. And then obviously the type is just going to be the same type as the fruit. So that's our first sliced fruit. And let's actually finish filling out this flight path. So this is going to be the current angle. This is the current position. And the angular velocity it's going to be the current angular velocity. But we're going to go ahead and just nudge it slightly. Just because, when you hit something with a sword, it's probably going to, rotate slightly differently. And then for the velocity, we're actually just going to reset the velocity to a whole new value. So again, hitting something with a sword has a tendency to, cease the current motion and sort of start a new motion. So, all right, so let's add a second piece of sliced fruit. So this will just be our second slice. And for this velocity, instead of moving to the left, I'm going to move to the right. And yeah, everything else I think is good. All right, and then at the end of this, inside of this set state, we're just going to make sure that we remove where, and to remove contains the element. So we're just removing from fruit where it's in this to remove list. All right, so now that we're populating our sliced fruit, let's go ahead and actually display them on the screen. Here is where we are displaying our pieces of fruit. Let's also display our sliced fruit. And we're going to also use our flight path widget. No reason not to. Remember the key. Now the child here is going to be a clip path, like I mentioned earlier. And we need to create a new clipper. We'll call it fruit slice path. We'll just create this in just a second. And the argument to this is going to be the slice itself. So this is going to be a simple class that just creates a path out of this list of normalized offsets. And I'll show you how to do that in just a moment. But first, let's add the child to this clip. And it's just going to be get image widget, pixels per unit. Perfect. All right, and then we want to also use our on-off screen. And just like the fruit, we're going to go ahead and set state. And just say sliced fruit remove SF. Okay, we have to implement this or create this fruit slice path. So it's pretty simple, so I'll just do this. Let's do this outside of our current class. And then this is going to be a custom clipper of type path. We can implement these methods. Should reclip, we can return false here. No need to reclip. And then get clip. So this is just going to be pretty basic. As I mentioned, we're just taking our list of offsets, which are normalized, and then we're converting them to a path. First thing we're going to do is move to our first offset. And since these points are normalized, we need to multiply them by the size. And then we'll just iterate over the rest of the points. And skip the first one because we already dealt with it. My brain wants to refer to this as normalized points for some reason. So for each of these, we're just going to say line 2. And then we're just going to return the closed version of this path. And close just does actually what we did before. It just adds the first item back to the end. So if it's an incomplete polygon, it just finishes it. So we got our fruit slice path, and we're doing our clipper. Sorry, I'm scrolling around like crazy here. So for each of our sliced fruit, we're just gonna display clip path, and it's just gonna be the clipped version of our fruit. So we can go ahead and see if this works. Let's restart it. All right, so this works pretty well. One final thing that I like to do is just increase the size of the slice, because sometimes you just do a little slice, but it's a poor user experience if like a little slice doesn't actually slice through the fruit. So you just want to take the actual slice and extend it on either end. And one simple way to do this, you might even say naive way to do it because it doesn't work in all cases, but works good enough for me. You can just take the world begin, extend it in the negative direction, and then take the world end and extend it in the positive direction. And this will basically triple the length of the slice. So if we reset our game, now you can just do slightly smaller slices and it'll actually, I don't know, it kind of feels like a sword. So pretty cool. So let's now show you the finished product. All right, so this is what's actually in the repo if you go ahead and check it out. So as you can see, it's basically what we just did. I just added a little slice thing. You can see where you're slicing. That's super easy to do with just a painter, a simple custom painter, drawing a path. I'm not going to cover that because we've covered custom painters like a million times. And I'm just keeping track of the score here. This is also pretty straightforward. If a fruit falls off the screen, you can see that this not sliced increments. Meanwhile, if I slice fruit, you can just see that the slices increments. So that's about it. I hope you like this. Super fun game, super fun to make. If you enjoyed it, please like and subscribe. Tell your parents about it. Tell your kids about it. And I hope to see you in the next one. Bye-bye.